Hi, my name is Maria DeBruin, and today I'm going to be teaching you a science lesson right from my home. Not only am I a teacher, but I'm a scientist, a mom, and a wife, and today I get to be all four of these right from my home. And the best part about it is I get to wear my slippers throughout the entire process. I have a lot of help with me today. First up is Leah. She's in 3rd grade, she's 8 years old, and she attends Old Mill Elementary School in Wall. Her teacher is Miss Turner, and she misses her class so much. Leah likes to play soccer in her spare time, and her favorite subjects are math and science. Next up is Luke. Luke is 11 years old, in 5th grade, and in Miss Buckle's class at Old Mill Elementary School in Wall. His favorite subjects are PE, and he loves astronomy. In his spare time, Luke likes to wrestle and rock climb. Then we have Grace. Grace is in 7th grade at Wall Intermediate School. She loves all of her teachers and really misses being there. Her favorite subject is science, and she also loves to wrestle and play lacrosse. Next up, we have my husband, Jason. Today, his job is cameraman, and he's recording for us for the entire show. He likes to garden, and he likes to bike ride with his family. Last up is Lainey Doodle. She's probably the star of the show. She's a 1-year-old golden doodle who we all love. She's going to be in the show later on, so keep a lookout for her. Now that you met all of my help for today, let me tell you a little bit more about myself. I love everything outdoors, especially running and racing in triathlons. I also like to bake and often bake elaborate cakes for my friends and family. Our whole family enjoys skiing, and we always try to pick the highest peak to ski from. And we like to hike. Here we are in Arizona on Devil's Bridge. But most of all, I love doing science and science tricks for anyone who wants to watch. I put on science shows all over. Maybe you can ask your principal to have me come to your school. So today you're going to learn about the scientific method, you're going to learn about states of matter, and then you're going to understand how matter undergoes changes, both physical changes and chemical changes. And near the end of the segment, we're going to play a really fun game where we have to make choices between those physical and chemical changes. We're also going to have some fun doing a demonstration at home that you can participate in. You'll need to get some supplies ready, so take a look at this list and see if someone can help you get the supplies ready for the end of the segment. Our supply list includes vinegar, baking soda, a disposable water bottle, it could be small or large, a balloon, same thing, can be small or large, and you may want to have a small spoon and a small bowl to help you with this experiment. For our second experiment, you'll need 1 plate. It could be a glass plate or a throwaway plate. And you'll need milk. The higher the fat content of the milk, the better the experiment will work. You'll need liquid food coloring drops, or if you don't have that, you can use pepper, dish soap, any kind will do, and some cotton swabs. I'm excited to learn with you and teach you today, so let's get started. So the first part of our lesson today is learning or maybe relearning about the scientific method. And I have my students here that are going to help me. Before I even talk about what this part of the lesson is about, I want them to actually see what they already know. And so what I have on these cards are the steps to the scientific method. Now you may have heard of the scientific method before, and your teachers may have taught you maybe different names for the steps, but they all sort of mean the same thing. So I'm going to give each of my students these cards, and I'm going to ask them to put them in the order that they need to go. So there's a step 1, 2, 3, and 4. So my students that are at home, I want you to look at these cards and try to order them correctly. So the first card is going to be hypothesis. The next card is going to be theory. The next card is observation. And the last card is experiment. Now those are not in the correct order, but I want my students to try and put them in the correct order. So you at home, take a look at these cards, and I want you to try to put them in the correct order while my students are putting them in the correct order. So let's see what they're going to do. So we have 4 different steps, and we're going to see if they can put them in the correct order. At home, I want you to look at these and think about what order you think they go in. Maybe you can write it down. Grace has theory, observation, hypothesis, experiment. Leah has observation, hypothesis, theory, experiment. Luke has observation, hypothesis, experiment, theory. So take a look at these words again and decide at home what order you think they go in. So one of my students has the correct answer and the other two are going to get a chance to retry it. You may have come up with the right answer at home as well, or maybe you needed to retry also. But you need to understand what the words mean first for the scientific method. So we have the 4 different words here, and I took Grace's cards to describe the words to you and see if they can help you either check your answer and make sure it's right, or maybe rearrange your answer. So the first word I'm going to give you is observation. When we have an observation, we are using our senses to come up with information about the things that are around us. I bet you know what your 5 senses are, and we're going to touch on those later on. But we have sight, we have hearing, we have taste, we have touch, and we have
smell.
The next word that we have is hypothesis. A hypothesis is an educated guess. And it's essentially when you're trying to figure out why you think something's happening. The next word we have here is theory. A theory is also maybe what your teacher might call the conclusion. It's where you kind of come up with the ending of everything and you decide what your experiment and your hypothesis and what all of your tests showed you. And so theory would maybe be something like the conclusion. And then we have the word experiment. Experiment is when we test something, when we come up with a plan and we design the test to see if we're right or if we're wrong. So now using the definitions that I just described to you, I'm going to ask my students to take back, Grace is going to take back her cards, and I want them to look at their words and see if they need to either change them or if they want to keep them. And so you at home, now thinking about the definitions of the words, I want you to decide what the correct order should be. So take a minute and take a look. Was yours right? Or do you need to take a few seconds to move them around? Okay, let's see if you were right. So Luke was the one who had the right answer. Well done. So it looks like Leah now has the right answer, and it looks like she switched from her answer before, the experiment and the theory. Leah, why did you switch those?
Well, I switched theory because once you told me the definition of it, I realized that was conclusion, and conclusion is the end, so I put it at the end. But then I decided to keep these 2, and then the only spot for experiment was right here, so I put it there.
Perfect. So it looks like Grace now has observation, hypothesis, experiment, and theory, which is correct. Grace, can you tell me why you put observation first?
I put observation first because I realized the only way you can start is if you have information, and observing things, you gather information.
Great. So let's look at the steps a little bit deeper. You heard what the definitions were earlier, but now let's try to apply them to the steps of the scientific method. The first step has to be observation, because you need to use your senses in order to decide what is the problem. You can definitely make observations after the experiment portion of the scientific method, but you do need to use them first so that you know even what your problem is. The next step is hypothesis. This is where you make an educated guess about what you're observing. If you have a problem and you want to solve it, this is where you decide how to solve it. And then next, you're going to test it by running experiments. You'll see if your hypothesis was right or wrong based on the results that you get from your experiment. And the last part is theory. And the theory draws all of the information that you have together to come up with a conclusion or an answer to what you think is the correct reason why your observations are behaving the way they are. So we have observation, hypothesis, experiment, and theory. Well done. So now for the next part of our lesson, we're going to focus on observations. We touched on what they are is essentially using your senses to come up with information, and we talked about what those 5 senses are. So let's just remember them. Let's see if you can do them at home. They are, in no particular order, sight, hearing, sound, right? Smell, taste, and touch. And so we're going to use those in our lesson today to make observations about the things that you're going to see in these videos. So now we're going to play a game, and you have to try and guess what sense you're using when I do each of these demonstrations. So here's our first demonstration. What I have in this glass is vegetable oil. But what you probably didn't notice is that I had a glass vial hidden inside of it. And so this trick is pretty amazing because the glass becomes invisible in the vegetable oil. You can do this at home with vegetable oil that you already have, and all I have is a regular glass, and then any small glass object will work, but it has to be glass in order to become invisible. Can you see as that goes into the vegetable oil, it actually disappears, and when I drop it in, as long as there's no air bubbles, it's gone. The reason why that happens is because vegetable oil and glass have the same refractive index. That's a really big word for basically saying how light shines through an object. So light shines through vegetable oil and glass in the same way. So they look invisible when they're next to each other. So what sense did you just use when I did this demonstration? So what do you think? That's right, you used your sight, because you had to see that the vegetable oil was actually hiding that glass in there. Well done. This video is taken from my classroom. I had a 10-gallon fish tank filled with vegetable oil, and we placed this beautiful glass vase inside. The reason why I chose it is because it was really thin glass, so it was disappearing in the vegetable oil very easily. Thick glass sometimes is harder, as you can see the air inside of the glass. The edges here are disappearing as the air bubbles go away. It's completely invisible. And all you can see is this hand holding something, but you can't quite be sure. And then you can see as it comes out, as the vegetable oil is pouring out, it's completely visible again. This is a pretty amazing trick. So now for this next demo, I'm in my bathroom, and I'm going to spray my favorite perfume. So what observation would you use if you were in the room with me right now? That's right, you would be using your sense of smell. And you would say, oh, you smell so lovely. Or maybe you would say, oh, that smells awful. But in any case, you'd be using your sense of smell. For this next demo, I'm going to ask my sweet dog, Lainey, to come and help me show you this sense. So what sense am I using when I pet my really sweet dog, Lainey? That's right, I'm using touch, and she's really soft to the touch. Maybe you have a pet at home, and maybe they feel wiry or rough or soft, but you use your sense of touch all day long to gain information. So this next sense, I'm going to show you it with ice cream. So one of my favorite desserts is ice cream, and in our house, we eat it out of a mug, probably because it looks secretive, like you're not actually eating ice cream. But what sense am I using when I eat ice cream? That's right, taste. Leah's sleeping. Let's see what sense she's about to use. Did you guess hearing? So hopefully most of that was really review for you. And now you remember the information about the scientific method, and you remember the information about using your senses to gain information. And now we can get to the really fun part of this lesson, which is understanding the differences between physical changes that happen in the environment around us or chemical changes that are actually happening around us. And to understand the difference between physical and chemical changes, we have to really think about what's happening to the substances themselves that are involved in those changes. A substance you can think of as a bunch of atoms put together to make up molecules or to make up even bigger things. Things that are around you all day long, like water or the food that you're eating. And so when we have to look at those, we have to understand what their phases or their states of matter are. And we have 3 states of matter that are around us. I bet you know them. Go ahead and say them out loud or tell someone who's sitting with you what they are. They are solid, liquid, and gas. I bet you knew that. But in order to really understand how solid, liquid, and gases behave, it would help to look at some examples of those. And so the first example that we're going to do is actually move our bodies in the way that solids, liquids, and gases actually move. So I want you to get up off your couch and get ready to do some moving. So this game, we're going to behave like the phase that I tell you. So the first phase that we're going to look at is a solid. When solid molecules are together, they are very tight and close together and they don't move. Very, very little movement really, but not that you could see. So right now we're behaving as a solid. The next phase that we're going to look at is a liquid. Liquids still hold on to one another, but they move a little bit further apart and they have a lot more motion. Okay? And then the last one is a gas. At this point, we don't hold on to each other at all, and we move around really, really fast because we're not supposed to be near each other at all. Gases just move all over the place. So now we're going to play a game where I'm going to show the card, and you at home have to behave like this phase. So the first phase, ready? We're going to do is a solid. Let's see if they get it right. They're holding on to one another and they're not moving. That's perfect. All right, let's see a liquid. Solid. Gas. Oop, gas. Solid. Solid's my favorite one at home. I hope that you got them all right. Good job. So a couple of nights ago in our house, we decided to play with a little bit of liquid nitrogen that I had left over from a couple weekends ago. In this demonstration, I can show you the differences between solid, liquids, and gases. I just dropped in a raw egg into the liquid nitrogen. A raw egg, obviously, is a liquid. You know that because it runs kind of freely and it moves around, just like we saw in the dancing portion of this segment. It has the ability to move while still staying intact. So right now in this video, the egg is freezing in liquid nitrogen. Liquid nitrogen is extremely cold because nitrogen exists as a gas at room temperature. And I purchased this liquid nitrogen from a local supplier, and you can see that it freezes the egg completely. In just a matter of less than 30 seconds, the egg is solidified. It is now a solid, completely hardened. Isn't that awesome? So now you can see in this next part, I'm actually turning the liquid nitrogen back into a gas. You can see all of that gas forming when I poured a little bit of warm water over top. In this next video, I'm actually using dry ice. Dry ice is much better to work with if you're going to do this with a parent or an adult at home. Liquid nitrogen is not to be used by anybody except for a trained scientist. If you can get some dry ice from a local grocery store or a provider of dry ice, you can pour a little bit of warm water over top of it and see the same kind of gas form. But again, never touch dry ice with your bare hands. For right now, we're going to focus on gases a little bit more. Gases behave fast, they move around, they're really far apart from one another, and in theory, scientists believe that they don't interact. We call that an ideal gas because ideally it's behaving the way we want it to. But in reality, which is what we call a real gases do in fact kind of slow down and eventually they come together. And they obviously have to do that because at some point they need to liquefy, right? When we have gases like water molecules in the air around us, we know that in the morning time, we can see them actually come together and condense on the grass outside. So we know that we expect gases to really be far apart from one another, which is what we call ideal gases. But we also know that real gases do eventually come together, and they slow down in order to do that. So I'm about to teach you something that's really, really high level science, stuff that you would probably only learn in college. And even though you're in elementary school, I'm gonna still give it a shot because I have a really strong feeling that you're gonna understand this. It's called the Boltzmann distribution curve. And essentially what it says is that not all gases behave the way that we think they do. And so some gases are going to have a lot of really high speed, and some of them will have slow speed depending on temperature. And so I'm going to show you what that graph looks like. You didn't know that you were going to be learning about graphs today, did you? Even though this is a science lesson, we use math very often in our calculations and our understanding of science. And so what I have here is the Boltzmann distribution curve, and it's basically showing you that speed is increasing from left to right, and the number of particles is increasing from the bottom to the top. And so you can see that as the speed is low here, most of these particles have that speed when they're cold. The room temperature particles have a greater distribution. That means that they're more spread out. So some of them are moving slow, and some of them are moving fast, and some of them are moving right in the middle. Whereas hot particles have a much greater distribution. That means that they're spread out very far. Their speeds could be very slow, and they could be extremely fast. And some of them are hanging out around here. But our cold particles mostly do all the same thing. Our room temperature particles are sort of doing the same thing, and our hot particles are really all over the place, not all doing the same thing. So let's take a look at examples of these. The first example I have is our cold particles. Obviously, this is ice, and we know that this is a solid and that these particles are very close together and that their speed is essentially all the same, right? If we look at our Boltzmann distribution curve, most of those particles have this speed, which is a slow speed. Now if we look at our room temperature water here, the room temperature water does have a greater variation in the speed of the particles. Now we can't see the speed of the particles, but we know that room temperature water will eventually evaporate, which means that the speed of the particles must be moving fast enough such that they break free from the liquid phase and go into the gas phase. And their distribution is greater, right? There's a greater variety of speed in the room temperature water. Now, maybe you could hear, but my water over here is boiling. This is the hot particles. These molecules are moving at a very fast speed to go into the gas phase. But not all of them are moving very, very fast, because if that were true, then this pot of water should evaporate and go into the gas phase instantly. If all of the particles were moving at the same speed, water would boil and be gone immediately. But remember, on the Boltzmann distribution curve, we have particles that are moving at all different speeds. The ones that are evaporating right now and boiling off are really hot. They are going at the higher speed. Over here, there's some particles that are going at a lower speed. Well, the easiest way to understand this is actually through dancing. So you guessed it, we're going to dance yet again. And you're going to see in this next set that you're going to actually be able to observe who's doing the slow dancing, who's doing the really high dancing, depending on the speed of the music. Remember that not all dancers do the same thing, just like not all molecules will do the same thing. Here you can see we're dancing to a slow song. During slow music, most people will dance slowly. But when the music speeds up a little bit, we dance a little bit faster. I'm dancing a little bit faster than everyone else, and Luke is still dancing pretty slow. Okay, now the music's gonna get really fast, and we're dancing much faster. I'm the craziest, and so's Leah, but Luke still is dancing really slow. This shows you how not all the particles behave. Oh, what happened to Luke? Well, as you just saw in that video, sometimes the fast particles bump into the slow particles, and the slow particles maybe just fell down. We did have to take a moment to pause in this video to talk to the fast particles about not bumping into the slow particles so harshly. All right, let's carry on. Throughout the video, Luke was the one that was behaving like a slow particle. He was always moving at the same speed. But then I continued to move to the beat of the music. I was getting faster when the music got faster, and then I was going really fast when I was playing that techno music. And then some of the particles, like Grace and Leah, were moving at their own speed. This is just like the Boltzmann distribution curve. The particles all don't always behave the same way. Sometimes the particles are moving faster, and sometimes they're moving slower. I told you this was really high-level science, but somehow I bet you figured it out. The Boltzmann distribution curve may be taught at colleges to college students, but you're in elementary school and you already understand it. You're super smart. So we just learned about the different states of matter, but now we're going to look at matter in a different way. I told you earlier that we were going to learn about physical changes and chemical changes, and that's something that we can examine because matter undergoes physical changes and chemical changes. Let's first understand what matter is. Matter is all around us. Matter is anything that has mass and takes up space. So I'm matter, you're matter, water is matter, the dust particles are matter. Everything that is mass, that has mass and can take up space is considered matter. And so now we're going to examine matter in terms of physical and chemical changes, but first we need to understand their properties. So matter has different types of properties. Properties describe the way it is. For example, the properties of you and I may be different because I have brown hair. My brown hair is a property of me. I have brown eyes. That's a property of me. What other properties can you think of when you think about ourselves? So maybe it's your skin color. Maybe it is the length of your eyelashes. Maybe it's your height. So all of those are different properties. Those are things that we can see, but things that you can't see maybe are like your blood type. And so properties are sometimes things that we can see about matter, but sometimes it's things that we cannot see. So physical properties are going to be the properties that give a characteristic of matter. Something like the color of that substance, or perhaps the melting point or the boiling point of that substance. Those are going to be physical properties. The other types of properties that we have are chemical properties. Chemical properties are going to specifically describe how that substance or that matter undergoes change to turn into new substances. So when we think about chemical properties, we can think about its ability to rust, or its ability to react, or its ability to decompose, and that means to break down and turn into something, into a different substance. And so we're going to look at physical properties and chemical properties in a bigger list. The physical properties that we have are color, taste, smell, and those are things that are common to some of the matter that you have around you every day. Like in your kitchen, we definitely would use color, taste, and smell. But some of the substances that we have, we can think of water has its own melting point. Sugar has its own melting point. Those are physical properties of those substances in particular, and they help us identify those substances. Boiling point is another type of physical property. So all of these properties help us identify that substance because those are specific characteristics of that substance. And you know what? These physical properties will never change for any substance. For example, we know that the boiling point of water is always 100 degrees Celsius. That will never ever change. Kind of like the color of my eyes will always be brown. That will never change. Those are physical properties of the substance. The chemical properties are the change of one type of matter into another type. So the substance is going to turn into a new substance. And some of the properties that we can think about are really like examples, is rotting, exploding, reacting, decomposing, rusting, and cooking. All of these examples will essentially change the original substance into an entirely new substance by undergoing these chemical reactions. So these are the two different types of properties that matter can have. So now that you understand what physical and chemical properties are, we can then examine what physical changes and chemical changes are. And so the way that you're going to do that is by using your senses, like we talked about earlier, to make observations. Now, of course, we're on video today, and so you can only really see what's happening, but we're going to get to a set of demonstrations where you're going to have to figure out whether or not the demonstration is a physical change or if it's going to be a chemical change. And so let's first discuss what physical and chemical changes are. Physical changes are when the substance simply undergoes an appearance change. It is still going to be the same substance that you start with. It may look a little different, or it may take a new form, or it could change its state of matter, but the substance itself will always be the same. Its properties will always be the same, and it's not going to turn into a new substance. One way that you can always know that a physical change is occurring is you can ask yourself, can I get the original substance back? And if you can, then it's going to be a physical change. It may look like a new substance, but if you can get it back to the original form, then it's just a physical change. For chemical changes, you're going to form entirely new substances. So a chemical reaction of some sort is going to happen where you form new substances entirely. So unlike physical changes where you can get the substance back, with a chemical change, you can't get that substance back. So you have to think about the examples that I'm going to show you and ask yourself, can I get this substance back or can I not get the substance back? It doesn't work for every scenario, but it's a really good, easy way to identify the difference between a physical and a chemical change. Let's get started. So we have here my three wonderful students again, and they're going to help us play this game of chemical or physical change. So Leah is going to remind us, if it's a chemical change, can we get the substances back?
Nope.
Oh no, right? Because they turn into new substances. In a physical change, we can get the substances back. All right, so let's take our first look at our first experiment, and we're going to see if it's a chemical or if it's a physical change. So first here, I have just a plain raw egg, and I'm going to now cook it. So we're frying an egg. Are we going to have a chemical or is it a physical change? What do you think, Leah?
Chemical.
How come?
Because if you do something with the egg, it can't go back to how it was.
Right, so it was a raw egg, but now we have a cooked egg. Good job, that's a chemical change. So cooking is always a chemical process. And what we have here is boiling water. So water boiling, Grace, what do you think water boiling is? Is it a chemical change or a physical change?
Physical change.
That's right. So it's a physical change because we can see actually the steam coming off of it. We know that the water is taking a new form, right? The state of matter is changing from a liquid to a gas because we've heated it. But we also know that if we trapped that steam, eventually it would cool down and it would form the liquid again. So the actual chemical molecule, water, H2O, isn't changing into a new substance, it's just taking a new form. Kind of like what I have here, which are the ice cubes. So ice cubes are just basically melting in here. Is this a chemical or a physical change? Luke, what do you think?
Physical.
That's right, because again, water molecules aren't turning into something new, they're just taking a different state of matter right now. All right, let's move on to some of the other examples we have here. I have a rotting banana. All right, pretty brown looking, right? What do you think, Leah? Do you think this is a physical or a chemical change? Can you get the original banana back?
No way.
So is it a chemical change or a physical change?
Chemical.
That's right. Good job, right? We can't get the original banana back, so this is definitely going to be a chemical change. Rotting is always a chemical change. All right, let's go to this one. So here we have some sugar and I have some water. And I'm just going to take a scoop of sugar and I'm going to pour it in. and I'm going to stir it up. So this process is called dissolving, right? And if the water is warmer, maybe it'll dissolve more. At room temperature, it dissolves a certain amount. And after it's dissolved, essentially you just see clear water again, right? So what do we think, Grace? Is dissolving sugar in water a chemical change or a physical change?
Physical.
So it is a physical change because we know that eventually if we evaporated this water completely off, that the sugar would remain in there. That's actually how you make sugar crystals on your candy, or you may have done this in class before on a string, but eventually the water will evaporate away and you'll just have your sugar crystals remaining. So when you dissolve something, you can typically get it back by evaporating the liquid that it was dissolved in. All right, moving on, let's do this one. All right, Luke, what I have here is just a pencil, and I'm gonna do a little something funny to his face, poor thing. All right, let's show the camera. So I drew a mustache on Luke's face. He doesn't actually have one. Oh, hi, Lainey. And let me ask you, is that a physical or a chemical change?
Physical.
Why is that a physical change?
Because I can just wash it off.
He can just wash it off, right? So it's definitely a physical change. All right, let's do this one. Hi again. All right, so Leah, I'm just cutting the paper. What do you think?
Physical.
Physical, that's right. Right? Paper, the actual substance paper, whatever it's made of, is not actually changing its substance into something new. Now, if I went and burned this in a fire, it would most definitely turn into a new substance, right? But just cutting something and making the shape change is just a physical change. Remember, we talked about physical properties, and the properties of this aren't changing, just the shape of it is. All right, so now if I take this same paper and I just write my favorite word on it, did I change the paper? I just wrote science in marker. I could have done crayon, paint, whatever I did. Did I actually change the paper, Grace? Did I change the paper?
No.
So then what must it be?
Physical.
A physical change. All right, now let's check this one. This one's always really tricky for students. Lighting a candle. All right, so a candle has a lot of things going on in it, right? What do you think, Luke?
Physical.
What do you think, Grace?
Chemical.
Leah?
Chemical.
Okay, you're all right. So there's two things happening here when you light a candle. When you light a candle, you are burning off the wax. The wax is acting as a fuel for this candle to continue burning. If there was no wax there, eventually the wick would just burn out. But the wax is acting as a fuel, and we know that eventually the candle will completely go away because the wax itself is going away. It's reacting with the flame and the oxygen in the air, and it's basically combusting and going away. But we also know that if we blow it out, the wax will re-solidify, right? It was wet and then it's going to solidify again. So saying it's a physical change is true because the wax was melting and then it just went back. But it's also a chemical change because it's what continues the reaction in the candle. And if that didn't happen, then we would have never-ending candles, right? But we know that we have to keep buying new candles because it is actually a chemical reaction as well. All right, our last one is going to be brownies. So here we have some brownies that we're making, and we're going to put them in the oven for dessert tonight, and we're going to check back on them in just a little bit to see if they are a chemical or a physical change. So let's just take a moment to check them out in the oven. Looks like the brownies are done. Can you smell them, guys?
Mm-hmm. Uh-huh.
Yeah. All right, so the brownies just cooked or baked in the oven. So all three of you, when we cook something, is this a physical or a chemical change?
Chemical.
Chemical.
Good job, guys. So I did say this was gonna be our last one for this game, but I thought of another really awesome one. And so I'm gonna have to put on some lab clothes and then I'll be right back. So you remember earlier we used liquid nitrogen in a demonstration with the egg. So we're gonna do it again to determine if this is a physical or chemical change. So if you take a look at this liquid nitrogen, you can actually see it boiling. But it's just at room temperature, right? It's not heated on a stove, it's actually boiling. That's because liquid nitrogen doesn't want to exist as a liquid at room temperature, it's supposed to be a gas. Nitrogen is a gas at room temperature. In fact, it's 79% of the air that we breathe. It's surrounding us all the time. And so the nitrogen that's in here is actually boiling and steaming, in a sense, off. And so this now, we're going to use the temperature at which liquid nitrogen boils to create essentially a liquid nitrogen cloud in my kitchen. And so we're gonna pour some hot water on this and actually see the liquid nitrogen turn directly into the gas phase. So at first I'll go slowly. Pretty awesome, huh? And now, let's make this happen even bigger. Let's give a countdown in 3, 2, 1. Awesome! So what do you guys think? Was this a chemical or a physical change?
Physical.
Definitely physical, right? We just did a change of state, so just from a liquid to a gas. Pretty awesome, huh? This next video was actually recorded in my classroom. What I'm doing right now is pouring a liquid over top of plain white sugar. That liquid is sulfuric acid and should never be handled by anyone unless they're a trained scientist and wearing protective gear, such as goggles, an apron, and gloves. The reason why I was using it is because I wanted to show my students this amazing demonstration. You can see right now that that liquid is actually turning that sugar a different color. There's a color change happening right now. And you can also see, as this is progressing, that you're gonna have bubbling forming. That's another observation that we can see with our eyes. As it continues to progress, you're gonna notice a lot of bubbling and steam. So that means this reaction is actually producing gases and it's very hot to the touch. It's also growing. Isn't that pretty awesome? It's producing what's called coal or carbon. And so the white sugar is turning into just plain carbon. So let me ask you, is this a chemical change or is it a physical change? I think it's pretty obvious it has to be a chemical change. It turned into an entirely new substance. So now it's your turn at home to try out some chemical and physical changes. Earlier in this segment, I asked you to get some of these materials together, and if you have them, you can do this with us right now, or maybe after the segment, you can get your materials together and you can give it a try. So the first one we're gonna do at home is a chemical change. And I'm gonna ask you to look to use your senses at home to make observations. This time you can use all of your senses because you're gonna be doing it yourself. So remember what we have here is vinegar. So you can just get this out of your cabinet and ask someone to help you. Just make sure that you don't get the vinegar in your eyes, and it definitely is gonna taste a little bit like vinegar if you put your fingers in your mouth or anything. So keep your hands away from your eyes and your mouth when you're using the vinegar. And you're gonna have some baking soda here and a balloon if you have one. Now, if you don't have one, that's fine because you can definitely do this and still see the chemical reaction take place. And I'm gonna use a spoon and a little bowl or dish here to help me get my baking soda in my balloon. So the first thing that you can do is pour a little bit of your vinegar into your water bottle. And so it doesn't have to be any certain amount, but a quarter full, half full even is just fine. And then I'm gonna take my baking soda and I'm gonna pour it into my dish. And I'm gonna do that so that I can easily use the spoon to get it inside this balloon. And so you might need someone to help you, and you might need to try and find a really little spoon. But I'm gonna ask Leah here to help me. So Leah, can you get that spoon and try to get some of that baking soda inside the balloon? And so we have to probably do a little bit at a time. And I'll shake it in there. So you can put it in the top and then, oops, just shake it in as much as possible. Okay. And you at home can try this too with someone. We'll take a little bit of time as we're doing this because we want to get as much baking soda into the balloon as possible. Grace, do you think that you can open the bottom of the balloon for us up a little bit so that we can try and get more baking soda in there? Good, don't pop it, yeah? If you don't pop it, then it might splash in your face. Okay, we'll get a little bit more. Here, try that again, Grace. That's great, girls. Thank you. All right, Leah, I think that's all that we're gonna get in there.
Okay.
And so we want to get as much of it down, and whatever we don't get in, we want to shake off the top, the excess. All right, so now we're going to actually see this chemical reaction occur. So when I mix baking soda with vinegar, you're going to see actually the gas being produced. And so the way that you can see a gas is by the formation of bubbles, right? And I want you to just observe this on your own or just watch this right now and maybe you can try it later. So I'm going to take the balloon and I'm going to put it over the top of my water bottle such that I don't let the balloon flip upside down here. So I'm keeping it off to the side until I'm ready to release the baking soda into the vinegar. All right, we'll do a little countdown. Ready? 3, 2, 1. All right, so let's take a look. What's happening in there? So we can see all of the bubbles, and all of those bubbles are forming gas. The baking soda and the vinegar are forming carbon dioxide. And I'm gonna just pop that off. And I actually blew up a balloon with carbon dioxide gas from this reaction. So you can carefully take it off, or we could just leave it. And we can actually tie this off and make the balloon. Pretty cool, huh? So you had the observation at home that we saw just now in our kitchen, and hopefully your balloon blew up as well. So this was an example of a chemical change. We changed those substances into something new, carbon dioxide gas. Pretty cool, huh? So now we're going to try out a physical change at home. Earlier in this segment, I asked you to get these materials. We need milk. The whole milk works best, but if you have 2% or 1%, that will work fine too. But always the whole milk with the more fat will work best for this experiment. We need some dish soap here, and any food coloring that you have would be great. Now, if you don't have food coloring, you could have pepper, which I hope that you have at home. We have some throwaway dishes, but if you have just regular dishes, that works fine. We have a Q-tip and then just some paper towels for any mess that we might have. And so we're going to make some observations about the way milk and the soap interact with one another. So before we start this, because you're gonna have a lot of fun just watching and doing this, is that you need to understand that milk and soap don't really like each other. So there's a lot of chemical properties about each of these and physical properties that will keep them away from one another. So it's not like you would mix two liquids together and then they would mix with each other. These two will not mix. And so we can see some really cool behaviors with the way that they interact or don't interact with one another. The food coloring and the pepper is simply there so that we can make the observation. Without the food coloring or the pepper, we wouldn't be able to see what's happening between the milk and the soap. So first thing we're going to do is we're going to pour enough milk into each of the plates just to cover the bottom of the plate. If you need help, ask an adult to help you. And then you're going to take your food coloring drops or your pepper, and you're gonna place just a few drops. Now, what always ends up happening is that the kids think the more food coloring, the better. But we know from experience that actually just a few drops looks a lot better than a whole lot of drops. So let's just let them have some fun putting different colors, food coloring. Luke chose green, Grace has red. So just a drop, oh, that one's dried. Just a drop here and there, not a ton. Leah, you're gonna try to cover all of the milk with pepper. Yep, keep shaking all over, everywhere. So Luke's making a pattern. Oh, keep going. Here, let's see if we just open up our pepper. And can I just kind of shake it for you? Thanks, Luke, for waiting. So this could work better. Instead of shaking, we're just going to cover the whole surface with the pepper. Okay, Grace looks like she's ready. Luke's just adding another drop right in the center there. Okay, so we're going to do this one at a time because we want to make sure that we can see the observations from the food coloring as well as the pepper. And so we're going to take just the Q-tip and dab the soap into the Q-tip. We'll just wait for Luke first. And then he's going to put it on his food coloring. So you're going to put it on each spot. This one is Luke's. Watch as he places the soap on the milk. It's pretty awesome that soap pushes all of the fat in the milk far away from one another. The food coloring, like the pepper, is just there for the visual effect. The soap and the milk try to stay as far away from one another as possible, and that soap pushes all the fat away. Here's Grace's, a really cool video of the way soap and milk interact. These are from my students in class. You can see that they have a little bit more milk and food coloring there, and I bought high fat content milk so we can really see a very cool demonstration. You'll see that it continues to spread all over as they each put their drops of soap onto their food coloring. So today we learned a lot of awesome things about science. We learned about chemical changes and physical changes. We started off with the scientific method, and let's see if one of our students can remember. So Leah, what are the steps of the scientific method again?
Observation, hypothesis, experiment, theory.
That's right. It's observation, hypothesis, experiment, and theory. So first, remember we learned observation. We use our 5 senses. Then we move to our hypothesis, which is when we take an educated guess about the problem that we're observing. Then we run an experiment so that we can decide from our tests what our results are telling us. So whether our hypothesis was true or if it was false. And then we come up with a theory, which explains what we observed. So since Leah got that one right, why don't you have a brownie since you earned that one? But Grace and Luke, you did such a great job today too, so you should have your brownies also.
Thank you.
And so the other thing that we learned about is we had to understand how matter also behaves. And so we looked at solids, we looked at liquids, and we looked at gases. And we actually danced our way through these, right? We looked at the way that the molecules behave when they're a solid, liquid, and gas. Then I taught you some really advanced science. Remember the Boltzmann distribution curve? Well, we learned about this and how particles, when they're cold, a lot of them behave the same way. Kind of like when we slow dance, right? A lot of people will slow dance to the slow songs, and those particles are all behaving the same way. Then at room temperature, when the music gets a little bit faster, not as many people are willing to dance to the fast songs. And there's some people dancing, but then there's some people who are just dancing crazy and not to the tone of the music at all. Well, then when we have those really, really fast songs, we have some people who will definitely still not dance, some people who are dancing to the beat, and some people who are dancing way crazy. After the Boltzmann distribution curve, we focused on physical changes and chemical changes, and we understood the definition of each of those. And then we moved to the favorite part of the lesson, which was physical properties and chemical properties. And we played a little bit of a game by looking at each of these experiments and demonstrations to make a choice between physical properties and chemical properties. I had a great time learning with you today and teaching you. I think we only need to do one more thing, and that's actually to give our cameraman his treat for helping out. The cameraman is, of course, my husband, Jason DeBruin. Thanks for learning with me. Hypothesis. A hypothesis is called an educated guess. The next word we have is hypothesis. Leah's sleeping.
And it's a book for your
We're
age.
making Dippin' Dots with liquid nitrogen that I had left over in the garage.
Chris, what is it like?
It's called
And we melted some ice cream.
Holy cannoli!